So we are here to talk about electrifying rail hubs and why the future of bus electrification.
We're looking at using electrified rail networks as an enabler for battery electric buses and electric vehicle charging, potentially with other energy recuperation technologies. And this is one of the technologies that will assist us in achieving this future vision of engineering net zero, which is becoming a very important topic here in Canada. I'm most familiar with work that was done by the LRT operator in Edinburgh in Scotland. There is a great opportunity to site bus chargers at combined transit terminals, where buses often wait for longer than traditional stops, which makes them ideal for boost charging to extend their range. The trains generate more power under regeneration. Local nearby light rail vehicles or heavy rail vehicles cannot use all of that power, and on a DC network that means the system is non-receptive, so it cannot accept any more regenerative power without increasing the line voltage to dangerous levels. So the brake system on the train then dumps the excess energy into the large brake resistor you can see to the right of the pantograph circled on the right hand picture. And as you can see here, the power under traction is approximately 1/3 of the power it can generate during braking. Now, depending upon the vehicle type and the receptivity of the system, the recuperated energy can range for lightweight vehicles from between 18 to 60 kilowatt hours per braking cycle. But that showed that even under the highest loading systems on their network, 14% of their regenerated energy was lost to heat. But over recent years, there have been techniques developed to capture that energy to be stored and dispensed later, and it boils down to three main types of technology. As an example, when there are no scheduled buses, then the energy can be prioritized to use the excess energy to return the energy to the contact line of the LRT or the power rail, offsetting its energy consumption. Conversely, when BEB demand for recharging is high, we can prioritize the stored energy for battery electric bus use. Typically, larger LRVs can consume up to 2 megawatts of power and return up to 3.3 megawatts of power. The high-performance short headway LRT systems adopt very powerful regenerative and rheostatic brakes for performance and cost reduction reasons. In the best systems, we tend to lose between 7 to 20% of the regenerated energy that could otherwise be captured.
So in order for us to do this and capture 3 municipalities and get their engagement through this process, it was really important for us to be able to do that. So we're going to fully electrify this route with 15 additional Nova buses, but it's their newer version bus with 275 kilowatt hour batteries. And so the beauty of that, the larger 275 kilowatt hour batteries, is that if any of the chargers are down, because we have chargers at both stations, then we have enough capacity to charge at only one end. And so there's sort of a built-in redundancy there, but also when we're looking at our service, if we're running a little bit behind, we can do what we call a turn and burn, and then just continue on and make up some time there. So we have two charging options, and one of them is a depot charging, where all our buses pull into the depot, and we usually charge at night. It's about a 4 to 6 hour process, depending on the state of charge of the batteries coming in. And we have en route or opportunity charging. It's sort of an interchangeable term. And then the buses that are operating on Route 100, they come out of our Hamilton Transit Center that I talked about. And we have these opportunity charges here located at our loops. So the power requirements for these chargers, by the way, is 450 kilowatts, which is fairly small compared to an entire 300 bus facility where we need to have the power there. And what we did was we determined that these two locations were optimal for not only the Route 100, but also for future growth of our system, because over the next couple of years, we have probably an order of magnitude 500 to 600 buses that we're going to be replacing. Of course, the station here is going to be one of the busiest areas for train and bus passengers, right? So that's critical. We have a large number of buses from different routes that pull into these loops and utilize these loops and picks up passengers and that type of thing. And we can charge many buses on different routes with just one or two chargers. So really something beneficial for us where we can maximize the use of the charger instead of sticking it on the side of the road, for instance, at a bus stop. If we can minimize that as much as possible, we'll be able to maximize our infrastructure for sure. So we're running dedicated feeds for charging right now, and that's one of the solutions that we're looking at doing. And we're also working with BC Hydro on time of use and reductions in rates as far as charging for infrastructure goes. So having that separate feed and separate meter, for instance, gives us that opportunity to have those negotiations and be able to determine exactly what the power usage is so we can get those reduced rates. You know, there's a couple of challenges that we have with respect to real estate. One of them is that even at our transit centers, for instance, if we're going to do the depot charging, you need to be able to get that technology in. And so that takes up some space. So our tracks, for instance, and so you're going to lose some space there. And we have 7 transit centers and we're at or near capacity on all of those.
So Australia has the world's highest proportion of what's called non-synchronous generation. So they have more inverter-based resources than any other country. And we're going to see an increasing use of inverter-based resources here as the energy revolution takes over, not just in our field of transport, but in the greater energy market itself.